today's lab is lab number 5, which is all about test benches. So we have essentially 3 tasks to do. Task number 1, the easy one, we just go to the lab 5 test benches folder located in the labs folder on the OneDrive mirror and pick up the 2 source files that are those 2 there, MoxFF and MoxFF Testbench. Just add them as existing files there and then perform a simulation. So if we do that and we look at what we have here, as I said earlier, the equivalent circuit is a fairly simple one. We have a 2-to-1 multiplexer which passes to its output either 4 zeros or A and B. So as you can see, that would be the combinational part of the code. This one here, which sets A and B when select is 1, so this branch, otherwise it sets all zeros. And then that is followed by a D-type flip-flop or register, since it operates on 4 wires. And essentially when the clock arrives on the rising edge, it then passes the information from the output of the multiplexer to its output. So it has essentially a synchronizing effect and only updates the output when the rising edge of the clock arrives. And that would be basically the flip-flop part, which is shown here. So as far as the inference of the hardware is concerned, things are quite clear. There are 2 distinct and separate parts which run in parallel, which then implement this particular equivalent circuit the way we've seen it. If we then look at its test bench, basically here we have the usual parts of the test bench, which start with an empty entity, no ports. We then define the design under test as a subcomponent of the test bench. We generate all the signals to match those ports, which can have the same name. The only care we need to take there is for the clock signal to be initialized, because when we generate the clock here, we do a clock equal not clock after 10 nanoseconds, which essentially generates a symmetrical clock with a 20 nanosecond period. So twice of those 10 nanoseconds. So the signal is in low for 10 nanoseconds, then in high for another 10. So altogether a 20 nanosecond period. We then also need to port map that design into the test bench, which just connects it to the test bench, and then basically we're ready to generate the signals. So the test bench that we already have generates the signals that are shown in here. And if we want to perform task number 1, which asks us to carry out the simulation, we need to make sure we are in the sources for behavioral simulation there, select the test bench, and then simulate behavioral model. And that will basically show us the simulation, and that will look something like this. So it's a fairly small one, as we can see. We can zoom in a bit, and this is what we see. So you notice that when select is 0, which is up to this point here, okay, first of all, before we move there, you notice that before the first clock arrives, our output there is in red, so it's all undefined, which is perfectly normal because of the flip-flop. We don't output anything until the first clock arrives. So that is the reason for that area, and that is perfectly normal. Then for as long as cell is in 0, when the first clock arrives, we are going to output always 0. So up to this point, our output is meant to be all zeros, exactly as is shown in here. Then our A is 0011 and our B is 0101. So what's happening here is that from that point onwards, but notice that those two occur at the same time. So essentially, it will not register until the next rising edge of the clock, which is why we always should avoid this sort of situation that the clock arrives before a signal is settled. So that's why basically we only see that change in the output here, and then this one and that one, which are matching, lead us to an output of 0001. And then again, here we have the next rising edge, which the signal again hasn't quite settled yet, so it's deemed to be still 1, which is why we have now 0100 in here, because the new value of A is 1110, and if we AND that bit by bit with 0101, it matches that one and this one here, and that's why the output is giving us that particular value. And then basically from the next clock onwards, our selection signal, it's all 0, so that's why the output is all zeros. So that would be the explanation of the test bench, which we simulated as part of exercise or task 1 of our lab exercise number 5. So that was part number 1 for today, task number 1. Task number 2 was just to play with some other type of signal generation syntax in our test bench, just to get familiarized with what we can use inside of test benches to improve on that very simple test bench that we had to start with. And that was all about things that we've seen in lecture 11, which was the lecture on test benches. And as we've seen in lecture 11, here we're talking about using various forms of the wait statement. And in particular, we have wait for, which is introducing a fixed amount of time, or wait until, which introduces rather than an absolute amount of time, a relative amount of time, which is kind of synchronized with the clock. So we can use wait until clock equal 1 and clock event to wait for one rising edge, or we can use wait until clock 0 in clock event to wait for a falling edge of the clock. And in addition to that, we can use things like for loops and such. So those would be the kind of things to try for task number 2. And then finally, we had task number 3, which was the more substantive task for today. And that was to modify this test bench that we had available in order for it to generate inputs which match the ones presented here. So let's see how we can tackle this one. As you can see, what we have here is the first signal change would occur 1 rising edge, 2 rising edges, plus 1 falling edge, and then half of a half period. Bearing in mind that as we've seen from our test bench, half of a clock period is 10 nanoseconds, then basically we're looking at an additional delay of about 5 nanoseconds to match this particular diagram. So basically we're looking at 1 rising, 2 rising, plus 1 falling, plus about 5 more nanoseconds to generate that change in cell. Then we need to wait 2 more rising and 1 falling. If we were to look at a relative plus 5 nanoseconds to instill change number 2, which is a change in A from 4 zeros to 0110. Then again, we want to wait 2 more rising and 1 falling plus 5 nanoseconds, and that will take us to change number 3, which is to change B from 0000 to all ones. Then again, as you can see from the diagram, 2 rising, 1 falling plus 5 nanoseconds, and that takes us to change number 4, which is again a change in A from 0110 to now 1001. And then a similar pattern occurs, basically 2 rising edges and 1 falling plus 5 nanoseconds, then change number 5, change number 6, number 7, 8, 9, and then for 10 we have to wait a bit more, so we have to wait 1, 2, 3, 4 rising edges, 1 falling, plus another 5 nanoseconds to then finally change B from all ones to zeros at point number 10. So that was basically what we had to implement at task number 3. So to show you what I've done that as a separate file. So I still have my original multiplexer there, but then the new test bench is shown in here. So basically what I've changed there is the signal generation part, the user generated part of the signal generation part of the test bench. So I've set the initial values, cell 0, A all zeros, B all zeros, and then the first change happens after 1 rising edge, 2 rising edges, and a falling edge, plus 5 nanoseconds, and then I put cell in 1. And then I did the same for the second, third, and so on, exactly as discussed in there. So in my case, rather than using a single wait for, I've used, which would be a absolute type of delay generation, I've used relative as much as possible. So basically synchronized with the clock and then added those 5 nanoseconds as an absolute value before making the changes. And for the last one, basically I've waited 4 rising edges, 1 falling, plus 5 nanoseconds before changing B for the last time. And then if I want to simulate and to see if that is indeed correct and matches what the requirement was, of course, we can always check the syntax of the test bench to make sure there are no issues. And in this case, there aren't. And then basically just simulate behavioral model. So if I do the simulation, then this is what I get. So let me zoom in one step so we can see things better. And I'll show this in parallel with the, let's try to bring them in sync. So in parallel with the second diagram, let's show them exactly in the same format. So here we are, I'll hide the output like that. So you can see that the first change occurs exactly as intended, 2.5 plus, or roughly 2.5 clocks after. Then we have change number 2, then we have change number 3, 4, 5, 6, 7, 8, 9, and then finally change number 10. So that's pretty much exactly what we would expect. And then in terms of the behavior of the actual simulation, looking at what's happening here, and it might be easier for that to just kind of compress them. So up to when the first clock arrives, the output again undefined because the flip-flop doesn't let anything pass until the first clock arrives. And then up to this point, my selection signal is in 0, which means that the output needs to be 0. And you can see it is 0 up to that point. Then at this point, we are changing the value of cell from 0 to 1. And you notice that now that is done earlier than the clock arrival. So cell has time to settle. So basically when the clock arrives, cell it's already 1 and it will do A and B. But A is in 0 up to that point. So at least up to that point, OP still needs to be 0, which is correct. But B is still 0, at least up to that point. So at least up to that point, we would expect A and B to be still 0, because obviously ANDing with 0 always gives 0. And in fact, it will only change when the next clock arrives here, because of course that output is not passed or updated by the flip-flop until the clock arrives. So at that point, since cell is 1 And since what we have now to AND with is 0110 ANDed with all ones, that would give us 0110 in terms of the output, but that output again only changes when the rising edge of the clock arrives. Then the next change in A is here. So the new value of A is 1001. 1001 ANDed with 1111 gives us 1001. But again, that only gets updated when the next clock arrives. And so on and so forth. You can just follow the same reasoning as before. You notice that at that point we are changing cell back to 0, which basically gives us an output of 0. Again, that only happens when the clock arrives, and it's only going to be reflected at the output when the clock arrives, once cell has been changed to 1 and we start doing ANDing again. So that works exactly as intended, and that's pretty much what we had to do today. So really the idea is that all the changes that we make in a test bench are really after the begin of the signal generation part of the process and before the final wait, which is the wait forever that we must have just before we end the process. And this is the part which the user needs to generate themselves. So that is the unique part of the test bench. Otherwise, clock generation and components and signals, that is pretty much similar or the same for all other devices. The only thing which the user needs to set really is pretty much those values that can be done in two different ways. You can have either absolute measures like wait for, or you can have more relative type of statements like wait until clock event and clock equal 1 or clock equals 0, and you can have as many of them as you like. Of course, if we wanted, we could have used a for loop there for those 4. I could have said for 3 to 1 or 3 to 0 to have 4 of them and put a wait until clock event and clock equal 1 inside of it. And that would have basically been slightly or led to a slightly reduced word count as far as the code is concerned. But other than that, fairly straightforward stuff. So those would be the kind of statements that we tend to use inside of test benches.